now we discuss large negative x. So as I mentioned earlier, so when x rotates counterclockwise, the steepest descent direction rotates clockwise. So when x becomes negative, then the steepest descent direction points to the right. So what is happening? This contour. So in order to find the asymptotics, we rotate it up to this vertical direction, and then, well, we have two choices. Well, actually, the truth is that we need to slip onto the Riemann sheet below our first Riemann sheet. So what is the correct deformation of the contour is going to be like this. So it's actually, it goes into the steepest direction here, but on the lower Riemann sheet. But then the problem is that it's infinite, right? So in order to deform it this way, it has to cross another branch point, t is equal to I. So to avoid this, the contour should return to this another branch point, then circle around it, and then move, then slip it back to the upper Riemann sheet and go into this correct steepest descent direction. So this is the correct deformation of the contour, right? So this part belongs to the lower Riemann sheet, and this one, the straight lines, the solid lines, belong to the upper Riemann sheet. So another possible interpretation of the same thing would be just to deform the branch cut. So make it, how to say, obey the direction of the steepest descent. So what you can do, you can draw a branch cut like this. So you bend it into the steepest descent direction. Well, this is suitable. You don't have to think about the lower Riemann sheet. But of course, when you bend the branch cut, you still have to keep in mind your initial condition for the definition of the g of t function. So it's positive when the complex t is to the right, or sorry, to the left of this initial position of the branch cut. Okay, so let's now, so this is quite unusual deformation. Well, that's the first time we encounter something like that. And let's see where this leads us to. So now, obviously, our asymptotics will include two contributions. The first contribution is the standard one, the previous one. It comes from the lower branch cut, right? So we already computed a contribution from it before, so it's going to be the same kind of thing. But now there is additional contribution from this second loop integral, which is slightly probably reminiscent for you of Hankel type contour. But the Hankel type contour was directed to the left. This one is directed to the right. But it's the same gamma function type contour. Okay, so here we go. First, let's address contribution from the lower branch point. Again, we expand our exponent function and g function in the vicinity of minus I point, and introduce the shifted variable s, minus I plus s. And okay, here is our integral. So s changes from 0 to plus infinity. Dt is equal to ds e to minus xi plus xs, x is negative now, divided by square root of 2s. And now, okay, so we need to define correctly the argument of this g of t function. So on this line, it was positive, but now the argument of the t plus I factor here is changed by pi by 2, sorry, by minus pi by 2. So here we have an addition of e to minus I pi by 4. So what is happening is we add here plus I pi by 4 since we switch into nominator. Right, so this is the contribution from this minus I point. Okay, yeah. Now the contribution from the I point. So the counter returns from plus infinity and circles around this point. So how do we compute it? So for this point, we introduce another change of variables, which is t is equal to I plus s again. So it's almost identical. So now you have the integral, this time from plus infinity to 0. Yeah, ds again over square root of 2s e to xi plus xs. And again, we need to define correctly the argument of this g of t function. So here we go again. So the vertical direction here, it was positive. And when we on this horizontal line, the t minus I factor, he changes its argument by plus pi by 2. So we have the addition here pi by 4, since it's square root, and minus pi by 4, since we switch to denominator. And we make a full rotation. And again, it's this t plus t minus I factor, which rotates by 2 pi from this direction, or 3 pi by 2 from the initial vertical direction, 3 in their clockwise direction. So the change of the argument is minus 3 pi by 2. Square root gives us minus 3 pi by 4, and in the end, we get the integral from 0 to plus infinity ds over the square root of 2s e to minus, ix, is plus sign, plus xs, and plus I 3 pi by 4. As we expected, well, the total difference between these two actually integrals is just the change of sign, right? So minus pi by 4 and 3 pi by 4. So this integral is again, as well as this, both of them are reduced to gamma functions, but they are identical. So we just, if you sum them up, we just get the doubled second integral, right? So the answer for this is just, okay, let's write down the full answer now. So the full asymptotics now reads, so the first integral gives us the gamma function of 1/2, which is again square root of pi, so it's square root of pi by 2. And as you remember, when after the appropriate change of variables, you will earn the modulus of x in the denominator. Indeed, because the correct change of the variables would be, since this x is in fact minus modulus x, then you just change the variables. Modulus of xs is equal to, I don't know, p, for example. And then you get this modulus x in the denominator. All right, so here is the contribution from the lower branch point, which is minus xi plus I pi by 4. And this is, right, this is the contribution from the second, the upper branch point, which is 2a square root of pi by 2 modulus x times e to ix plus 3 pi by 3 pi by 4. But actually, let's make it minus I pi by 4 and put minus sign here. Right, so what lesson could we learn from this? As you see, apart from the contribution, you kind of expected, because before, when x was positive, you got very similar answer, right? But the sign was different, so instead of modulus x, you got just x under the square root. But after x is rotated, x is changed to modulus x times e to I pi. And basically, this contribution is the analytic continuation of the previous answer for positive x. But apart from this, it's quite, I would say, counterintuitively, you'll get additional contribution, which popped out of nowhere. So this is actually a signature of a new phenomena, which will be discussed in great detail later. It's called the Stokes phenomenon, when your asymptotics sometimes change its behavior completely. So you get just full additional term when you just switch from positive values of your large values of your variable to negative ones. Right. And our last step is to fix this A integration constant. Okay, let's do this.